How do we know?
Howdy. Okay, it's my distinct honor to introduce our speaker for the distinguished lecture series, Rao Kambapati from Arizona State. So Rao is a very senior member of the AI community, and he has been a faculty member of computer science at Arizona State since 1991. And in his own words, he started as a quarter professor, then became a half professor, and eventually a full professor in 2000. And his current goal is to become two professors, but he wants to wait until the following season pass. Okay, so Rao has been very active in research in different areas, and his main research actually was in planning, and he has been doing planning, the traditional planning for decades. So I will not read his CV, his recognition, but to me, he has a lot of recognitions, including ACM Fellow, and actually Fellow and former president of Triple AI. But these are, to me, that's not important. If you know Ron, I think you know, number one, he's a very insightful person. So if you talk about him, about anything about AI, he has very deep insights. So just give you an example, if you know chain of thought, and Rao has a paper, the title is Chain of Thoughtlessness, analysis of chain of thought for planning. So there's a lot of insights in that paper about how and why and if COT works. So if you haven't read the paper, I highly encourage you to read that paper. So, and Rao is also a very passionate teacher. So I actually took 2 courses from him, and I learned AI from him. Like 16 years ago. But that's still everything still holds right now. So and Rao received the Triple AI Outstanding Educator Award this year. So that's a great honor. Congrats, Rao. So as I mentioned, Rao's research was in planning, and recently he became very interested in studying if and how language models can do planning. I think that's his topic today. So with that, Rao, stage is down. Thank you.
Okay, you guys can hear me? Okay, so about that, hoping to become 2 professors, I think after the breakfast and a huge big lunch, I think I'm very much on the way to becoming 2 professors if I don't fall asleep here. Okay, also thanks for showing up. Either you guys are just great at going to these talks, or LLM being present will bring people out of the woodwork in general. So anyway, I'll be talking about this stuff, but if anybody, a professor talks about their work, it's actually not the professor who is doing the work because they're out there giving talks or writing grants. It's the students, and those are my students who actually several of the work I'll be talking about. It turns out to be a very interesting thing that one of the guys who did a lot of this work is called Karthik Valmikam, and his brother is sitting here. So I told Karthik, you can tell me if I can take something and give it to him if you want. I can be the Amazon for you guys. But anyway, so it's fun, and it's nice to be here. It's great to be here, and I had a great time until now, and I'm hoping to have more better time, and at least make sure that you don't fall asleep. Okay. Okay, so going back to one other thing I want to say is I want to also say, since I'm from Arizona State University, by the way, your campus looks sort of very similar to me as our campus. It's very beautiful. I love it. And I do want to say something great about Arizona State University, but I don't need to. I mean, Shi Wang is here, and you already know he's our student, and he's an amazing guy, and I'm sure I can't add anything more than you already know having Shi Wang here. So let me try to get you to, I want to just quickly say a little about my background in AI, research background in AI, and then get into the main topic, which is LLMs and reasoning and planning. That's what we'll be discussing. It'll be a long talk, but hopefully I'll keep you awake. Okay, turn up the volume. So I just need to kill this, I guess. Okay. So yeah, so everybody is an AI expert. I think pretty much everybody in College Station is an AI expert, unless proven otherwise. Everybody everywhere is an AI expert. In fact, people have said that the fastest things in the world include actually people becoming experts in AI, and people becoming, and then so in fact, I say that I like to tell my intro AI students that the demand for AI experts without AI expertise has never been greater. Just never been greater. It's like a great time to say, I'm an AI expert, and you become an AI expert. Unfortunately, I'm a slowpoke. I've been hanging around this area way before it was cool. My first intro to AI course was actually using Patrick Winston's book, on whose name is this outstanding educator award that I got. And then so the stuff that I've been working on for a long part of my career has been planning and reasoning. How do you do, like the most important thing for the pink robot is, given the crazy environment that it is in, what do I do next? That's like the most important question that we always face. So planning and reasoning, and the planning depends on all sorts of interesting questions, such as the types of plans, the types of environments, the types of objective metrics, and so on. I spent a bunch of time working on those things. We can talk a lot more about that, if you are interested later on. More recently, in the last about 10 years prior to the last 3 years, I've been focused on, I and my group have been focused on explainable AI interaction. So if your AI systems are all over the place, they need to be able to work with you. So you need to provide advice to them in terms that you will provide to humans. And they should provide explanations to you the way humans will provide explanations to you. And so we did a whole bunch of work on that. In fact, there's a books that one monograph we wrote, and in fact, that's available online that you can get that too. Okay. By the way, I forgot. I was going to put a link to the slides. I forgot, but I will tweet them. And so if you are interested, you can always have the slides back later. Okay, so that's my background. But I'm not talking about this stuff. I can give you talks on this, but that's not what I'm doing today. Certainly, you're not here for that. You are here for this LLM stuff. Okay. And then, so basically, I want, I don't need to define what large language models are. Everybody knows what large language models are. I want you to start with, to have like a common ground for all of us. I want us to think about standard LLMs. Historically, that means almost as old as 2 years back, we used to have these things called GPT-X, Gemini, Llama. They still continue to exist. These are essentially auto-regressively trained on web corpora. The web was generated by you. Right? You didn't generate it for Sam Altman. You generated, you and your friends and your parents and your parents' parents generated web to actually deal with each other. We wanted to kind of, talk to each other about our knowledge, the human knowledge, right? Human cultural knowledge. And essentially, they then basically came in and trained themselves essentially on auto-regressively on the existing web. Okay, and I keep telling people, just to keep this in mind, that if Sam Altman already got all the money for getting all the GPU clusters from Satya Nadella, and he just needed the web that was missing, and if he said, hey guys, why don't you guys make up a web and put all the stuff that you know, it would never have happened. Web existed before you could do LLMs. Okay, this whole notion of data is being produced more. Data was always being produced. Even when we were in caves, we were producing data. We were not capturing it. Okay, and web essentially, and cell phones, all this stuff, captured the data that we were producing. And that was available, and so you actually were able to train large-scale auto-regressively. And basically, and of course, they may have been fine-tuned a little bit after the fact, so that they won't be particularly racist and sexist, although it's actually the more fun to be that apparently now. But you actually can do RLHF to kind of make sure that they're more palatable to the expected user population, okay? And then at the inference time, just complete the prompt. And this is constant time. And if you have to remember that is the prompt, many of you are computer science students, right? So computer science, we talk about complexity. A problem can have constant time complexity, polynomial complexity, semi-decidable, undecidable. Imagine you take an undecidable problem as well as a constant time problem, give both the prompts to these kinds of LLMs. Do you think that for the undecidable one, GPT-4 says, let me think for a while before I give the answer? No. As soon as you hit return, it starts spewing out. So you first have to understand that there's no reasoning going on at the inference stage because it's just right away putting out stuff, okay? So they were basically at the inference time, they're just completing the prompt. And that stuff already was claimed to be able to do planning, reasoning, everything. Part of what happened with this is even Dario Amodei, who did the first GPT-2 and GPT-3 training, probably didn't really realize how impressive they would be. Now, what are they impressive about? We did not actually expect that anybody can write essays that look coherent. Anybody can write answers that are in good style. And one of the things that I hope you will get out of this, if you haven't already heard it before, is LLMs are vibe machines. They get the vibe of everything. Okay, and for humans, actually, the style has been hard. Content was easy. In fact, the difference between us and Shakespeare is Shakespeare could write iambic pentameter. We could make stories like him too, but the guy could write iambic pentameter, you could. But now, who cares about Shakespeare? We have ChatGPT, it will make iambic pentameter. So in fact, in the past, if you gave, like a poem to your boyfriend or girlfriend, before ChatGPT, it meant something that you actually spent time. Now, if you give it, you say, okay, so are you paying $20 version or $200 version, right? So the style was always hard for us. Content was easy. So we assumed that if anybody can do style, they must also be good at content. Because that's how it is for us. Shakespeare already knew the stuff that you knew, plus he also could write iambic pentameter. ChatGPT writes iambic pentameter already, so he must know all the things that you know. That is the general cognitive flaw that we have. And so basically people made all sorts of claims, and that can actually be shown to be wrong. I will show that part of it, okay? Then, of course, in fact, these things, if they were doing reasoning, you wouldn't need a new kind of models. And in fact, you would have to ask, why were you guys saying LLMs can do planning? If they were already doing planning, why do you need O1 and R1? Obviously, they weren't doing planning. Right now, they look a little more like they might be doing. We'll talk a little more about that. Though these are the standard LLMs, plus two very important ideas, test time scaling and post-training. Test time scaling actually is very easy to understand. Okay, which is you think of LLM as generating a candidate solution, and a verifier in the loop checks whether the solution is correct. If not, it says try again. Until the verifier allows you to go out, it keeps going. If you do this, you will actually take more time if it's a harder problem, and less time if it's an easier problem. Test time scaling reasoning will come out pretty naturally. The other thing that happens is post-training. You all heard about DeepSeek. You also heard about O1, but we have no idea what O1 does because they don't write papers. Apparently in China, people still write papers. We have gone beyond that in US. So essentially, post-training is an interesting way of compiling the verifier signal into the generator so that it is slightly better at giving its guesses. This is what we will characterize. So if you understand this, basically the talk is kind of making you realize that these things actually don't do planning. And these things do better on the benchmarks, and I want you to understand why. It's not necessarily whether or not they're doing reasoning, but why are they doing better on the benchmarks? Okay, so the foreshadowed summary, because I might actually get only halfway through the talk, and then I want you to remember what it is that I want you to remember, is that LLMs trained just on the web corpora were known to have severe limitations on planning and reasoning tasks. This is well known, and we have written papers on that. But they could, however, be used as a generator in a generate test cycle with a verifier in the loop. We have this idea called LLM modulo framework, where LLM sits in the middle, and there's a bank of verifiers, and the bank of verifiers essentially can keep asking it to try more guesses until the guess becomes correct. So this is, you can think of this as a prototypical test time scaling idea. There are other kinds of test time scaling ideas. So we do that. Then improved reasoning abilities can be compiled into the base generator. So in the test time scaling, you are now able to get LLM to solve problems after k tries that it couldn't solve in one try, because the verifier is actually checking whether it's correct or not. Once it is correct, then you can remember the correct solution and you can fine tune the LLM so that it's more likely to provide those kinds of tokens for that kind of problem. Okay, that is essentially the notion of post-training. And so the improved reasoning abilities can be compiled into the base generator of LLM with either supervised fine-tuning or RL. And actually, there's a huge deal that DeepSeek says that RL is the reason they did well. And again, I will tell you that there's always a cheering section for RL in AI. RL is a great idea. And a whole bunch of people have been saying, now it's going to start working. Now it's going to start making a big difference. And if your thing works and if you say it's because of RL, you get a lot more publicity. And I will actually show you that there are reasons to believe that RL is not playing that much of an important role in DeepSeek. In fact, it can be iterative supervised tuning would have been just as good. So that's the RL and the post-training and SFT training. And then the other thing is with LRMs, with this test time scaling as well as post-training, they're still generators. There is no more guarantees. They're just more accurate in the post hoc evaluations. There's still no guarantee that the answer is correct. So just an improved generator, okay? So resulting LLMs still have no generator guarantees, whereas if you use it in this LLM modular framework, you will have guarantees with respect to the verifier, okay? And then finally, one long important thread that I want to get across in this whole talk is AI always, the original sin of artificial intelligence is anthropomorphization, because we think the only things that we know that's kind of intelligent is us. So we'll start actually looking at everything that we call AI program and start using words that actually would make things like thinking, chains, thoughts, reasoning traces. And the problem basically is many of the times those anthropomorphizations are actually wrong and get in the way of understanding what the LLM is actually doing. And it's a very useful thing to understand. So that's one of the things that I want you to get across. Okay, so if you want to read the bunch of papers we have, but if you want to read like 2 papers, this one is, both of them are actually commentaries on New York Academy of Sciences. One is, can large language models reason or plan? This is sort of about LLMs before O1, and it sort of gives you a summary of what you can actually expect. And this one hasn't yet come out. You're just seeing it right now. It'll be coming out next week, I think, on how do reasoning models reason. And so much of what I'm saying are kind of derived from this paper. Okay. I said in the discussion, in the title, that from system 1 LLMs, so system 1 plus 2 LRMs. So I assume many of you heard of system 1, system 2. It's become like a huge thing. And they are actually metaphors of talking about human reasoning, brought up by Kahneman. And system 1 essentially corresponds to reflexive reasoning, which is more or less as soon as you have the decision to make, you just reflexively make the decision. System 2 corresponds to deliberative decision making, deliberate reasoning. And interestingly, while humans are supposed to have both system 1 and system 2, and we combine them, like if you're trying to get out of the oncoming traffic, you don't stop and think what's the best way to get out of the oncoming traffic. You just run screaming, and that's system 1. And then system 2 would be, if you have 3 hours to make a move, don't just right away make the move without thinking, take the time. That system 2 basically is providing the deliberative part. We have both of them. If you think of normal LLMs, when I say normal LLMs, I mean essentially the GPT-4, not the O1 R1. They're best really seen as an external system 1s for the humanity at large. Okay, they've been essentially trained on all the data, all the knowledge, quote unquote, in whatever natural language expressed thing that entire collection of humanity has. Okay, and then they're essentially almost reflexively giving the completions to the prompts. Okay, and interestingly, when you talk to humans, how do humans impress you normally? There are two ways humans tend to impress you. One is, man, that person knows this. Like a doctor knows that this particular kind of funny spot with this kind of hair loss might correspond to this crazy disease. Which they knew, right? We are very impressed. The other is this poor guy, Andrew Weil, sitting in his basement for 17 years trying to prove Fermat's last theorem. Deep reasoning from a set of, short set of principles. One is deep, the other is shallow knowledge, with a large amount of knowledge. With humans, we are impressed with both. You are impressed with both the shallow, able to put together huge amounts of knowledge, and going deep in one direction. With LLMs, we tend to get the same way, but that's a mistake. Because for LLMs, they don't have the memory limitations that humans have. The fact that they can put together stuff from economics with stuff from frontier math to stuff from molecular chemistry is not surprising. It's because you wrote everything all of us knew onto the web. That's what I would expect they will be able to do. On the other hand, reasoning is not something that you have actually put on the web. That's why they do badly. You understand what I'm saying? So you are fine to be impressed with LLMs doing this, putting together pieces of knowledge in a shallow ways, because you will be impressed when humans do it. But I would say that that's not surprising for computer scientists. That should not be surprising because, hey, if you had infinite memory, you would all have been like that. If you had infinite memory and less bars, you would have been just like that. Okay? So that's the thing. And so the interesting thing about system 1, system 2 is, if you took intro to AI before the dawn of LLMs, much of what happened in the intro to AI is system 2. Essentially, you'll take a search problem, you take a planning problem, you take a CSP problem, and do reasoning, and essentially do online reasoning to come up with the answer. And you talk about how to do the search, how to do the planning, how to do the CSP, how to do all these reasoning things. Okay, and surprisingly, what LLMs did is, LLMs are the first time we had a pretty impressive system 1. We never had that. Okay, so what we have is system 1 only. Before, we only used to have only system 2. And so if you want system 1 and 2, you should put together both of them. And so it's actually useful to know what happened in the intro to AI. If you still take those courses, if you still take courses without LLM in the title, that's actually useful. Because the next way to improve LLMs will come from reasoning, and all of that was actually what intro to AI was all about. Okay, that's worthwhile to keep remembering. One other thing about AI that's kind of useful to keep in mind is AI has become an ersatz natural science. You have these huge, big behemoth models that we have trained, and we have no idea what they do. So you poke them and see what they do. So I'm walking around, I see an armadillo. I never saw an armadillo. It's in Texas, I guess. I'll poke it. If it doesn't bite me, then I'll write a paper saying this kind of a thing, when poked this way, does this. And if I'm in the beginning of the zoology, that will be a paper. We are in the beginnings of the LLM zoology. And so there's a huge amounts of papers that are written by poking LLMs in different ways. There is nothing wrong with it. You do want to understand how these large computational artifacts behave. What you do need is some empirical rigor. You can't right away run as soon as your prompt does something interesting and write a paper. You want to see how robust is that behavior? How brittle is it? Why is that important? It is important because of 2 reasons. One, of course, is this business about, actually, let me skip over this. Because of the fact that LLMs have this thing called jagged intelligence. That's what people have made up. They are amazingly good at solving, quote unquote, giving the correct answer according to you, for some very impressive problems that none of your classmates or even your professors know how to solve. But at the same time, they can fail on simple multiplication. Right? And so what happens basically is, when we talk about people, if you saw a kid who can do integration by parts, you would assume that they know how to do multiplication. And you would be right. Right? Because nobody starts integration by parts before doing multiplication. If you see a computer program that does integration by parts, it doesn't have to do multiplication correctly. So your assumptions that because it does this, it will do this, you have to be checked. And if you don't check it, it's because you anthropomorphize. You said people who do this can also do this, so it must be the case. So the usual thing you say is, what more do you want? It did well on frontier math, right? So that should be enough, right? But the point, of course, is that's not guaranteed. In fact, many things can be explained in the case of LLMs in terms of approximate retrieval. If you've seen the problem once before, or similar problems once before, it becomes easier to solve those problems. That's why you prepare for the exams. And you guys still have, life, and so you don't prepare for the exams the entire time. LLMs have no life. They have looked at all possible data beforehand, and they can compile as much of the reasoning as they want into memory. And so they can actually do many more things from retrieval. And that sort of a thing tends to be very brittle, and you can check that empirically. By the way, if you don't know this, this is a very useful paper that you should read. Artificial Intelligence Meets Natural Stupidity. It's a 1971 paper by Drew McDermott. And it's a lovely, lovely paper to read. It was written in a completely different age, but its lessons are still very relevant. Don't use anthropomorphized terms because it makes you think it is doing what you said, what the word said it is doing. So you say chains on thought, it's thinking, you'll start saying that, okay, LLM must be thinking because I said it is thinking. I said it's a thought, okay? So it's actually useful to use content neutral terms. Like one of the other bigger ones that we'll talk about is this reasoning traces. That's become very big with DeepSeek-like models. Call them intermediate tokens. Don't call them reasoning traces because I'll show you that they actually are not reasoning traces. They don't have any semantics. They can be gobbledygook and can still give higher improved accuracy in the results. So you would never see that if you already called it reasoning traces, you'll think, yeah, they must be reasoning because I called it reasoning traces. That's the first law of anthropomorphism. Okay, so the thing that I already mentioned was a couple of things to remember about normal LLMs is style versus content and form versus factuality. Style is, as I mentioned, hard for us, easy for LLMs. LLMs are generative learning systems. Generative learning systems learn the distribution of the data. Style is a distributional property. Correctness is an instance level property. So just because you got the style doesn't mean you definitely will get the correctness. So it should not be surprising that generative learners get the style and yet fail on the correctness, okay? The other thing is civilizationally, as I said, we always thought style is harder than content, so we just assume that if it can do style, it must be doing content correctly. And this is across the board true, including with reasoning traces, because why people say it is reasoning traces is because the traces look like what people might mumble when they are thinking. Like, let me think, oh, if I look at it in a different way, all this stuff, if I say it, it looks like, my God, this guy is thinking, right? And this LLM is thinking. If you actually try to make sense of it, how many of you have run a DeepSeek on any problem and looked at the intermediate tokens? How many? Okay. For small problems, it gives you 35 pages. Have you checked the whole thing to see if it makes sense? No. It's like, as I was telling somebody, imagine you have two students, you ask them questions, and there's a page that they have to fill. There's a box for the answer. There's also scratch pad stuff. One student just writes the answer. The other students write the answer as well as some gobbledygook in the scratch pad stuff. And as students, you know that it's much better to write some extra gobbledygook because professor will give at least partial credit, right? And the problem is, in most interesting cases, the professor also don't know what the correct answer is. The question then is, which student's answer are you going to believe? You are more likely to believe the person who wrote this gobbledygook in the scratch pad thinking, hey, they must have thought, they must have got the answer. That's a cognitive flaw. You don't want to write AI systems that will exploit our own cognitive flaws. It makes no sense, okay? So if the reasoning traces don't have semantics, don't call them reasoning traces. Don't make them look like reasoning traces by just using pseudo-English. So I actually, as much as I think DeepSeek R1 is a great contribution to LRM science, their mistake was not to stop with R10. R10 is great. But they said R10 in its new intermediate tokens has English as well as Chinese, and people don't like it. Which people don't like it, I have no idea. And so let's make it all be pseudo-English. Has that improved anything? No, it didn't improve anything. What it improved is, it improved the possibility that you will fall for this being reasoning trace. It's not reasoning trace, it looks more like a reasoning trace. That's a bad thing to do because that's actually exploiting the cognitive flaws. The other thing about LLMs is hallucination versus approximate retrieval. I would essentially, you heard these words, LLMs are essentially can be thought of as sort of n-gram models. And so they always index. Okay, I mean, so they always, they don't actually do exact retrieval, because they're not databases. But on the other hand, they're always hallucinating completions to the prompt, such that the completion is in the same distribution as the expected completions to that prompt. The fact that it is in the same distribution is style, not correctness. Okay, and so I would argue that it's better to say that LLMs always hallucinate, and sometimes their hallucinations aligns with your reality. And when it aligns with your reality, you give them points. But imagine cases where you don't know the answer. Then you have to trust the LLM. And just because it sounds like it's in the correct style, you give the points, that's a very bad thing to do. And you can actually show that, in fact, empirically, that it's a bad thing to do. Prompt engineering doesn't change this, And again, I'm sorry, this is not a contrary talk to some extent. All I can say is I have papers in the same places that you have read other people's papers. So these are all, nicely referred and all that stuff. But it makes you think in a different way about some of the claims. Everybody says all you need to know is how to ask nicely. Okay? The problem is, yes.
When you use listening, you're making an assumption of what listening is. Is that constrained by land or not?
So yes, I'll get to that, but the point, by most of the time, in fact, the word reasoning, I would argue that when people in LRM are using the word reasoning, they're mostly talking about formal reasoning problems, math, etc., for which there are formal verifiers. And it's actually better to stick to that sort of definition than what people might call reasoning, because that's a very ill-defined point. Okay, so math is certainly considered reasoning, plans are considered reasoning, schedules are considered reasoning, and you combine some of the formal and some of the informal stuff, and then you evaluate. And if, in fact, there is no verifier, you can't actually evaluate the correctness of the reasoning problem answers anyway.
Right, so when you say these traces, wrong.
I will get to that as to how, I'll get to that, as to why they're wrong. Okay, so the point basically here is prompt engineering would only help if you know how to tell the right answer from the wrong answer. Even if you don't know how to generate it, if you should at least be able to verify it. If not, it's not really improving anything. Most of the time when people say prompt engineering helped, it is for problems for which you didn't need LLMs to begin with. You know the answer. And you just want to make LLMs say the same thing. How many of you use Google to check whether Larry Page knows what you already know? That's like a silly way to use Google, right? You want to use Google to learn stuff that you can trust. You want to use LLMs and reasoning to make them solve problems that you can trust their answers without you necessarily knowing. Sometimes it may be harder to generate, and you can verify easily. But that's the most important thing. It's not that prompt suddenly changed it. It's just your ability to check is very crucially important. So my big contribution to this area is this, that I even actually sell on T-shirts. So outside, after this talk, I'll sell some T-shirts with this, saying, this is the old XKCD cartoon, where I just say, the impressive reasoning abilities of LLMs depend on the prompter knowing the answer, ultimately. If the prompter doesn't know the answer, then you can't just assume. And imagine asking Google factual queries for which you already know the answer. Why? You have no other life? Why are you doing that? And so why would we do this? So now that there's deep research, you can change that into impressive researching capabilities of LLMs, depend on prompter knowing the answer again. In fact, there are already examples of deep research producing research that is bogus. And most of us say, if it is in clear plastic binder, it must be research. And LLMs are amazingly good at putting everything in clear plastic binder, in the sense, very good style. But there's this particular guy, this particular tweet by Daniel Litt, he tried to do some small research on the demographics of people writing papers in annals of mathematics. it made up this beautiful research paper, bogus. It never even checked. There were like 1,300 or so, or maybe 1,500, 1,500, and 5,000 papers or something. It looked at 2 or 3 papers, and they just made up the rest. And he would not have known it but for the fact that the guy basically was skeptical and tried to check what was it actually doing. Do you understand what I'm saying? So human in the loop, LLMs are amazing. Otherwise, you should be careful. That's a T-shirt that I'll sell you if you give me good money. Okay, I was at ACL and I gave a talk on this. And it's kind of fun to go to natural language processing people and say, you guys have nothing much to do because LLMs are doing everything you do. I did that. So anyway, one crazy thing about LLMs is that, as I already mentioned, computational complexity considerations don't actually make any sense for LLMs, normal LLMs. It's not that they are solving harder problems by taking more time, which also means that if you think that LLMs can't generate the solution, maybe they can verify, that's a wrong intuition, because verification is reasoning. Okay? And in fact, you can show that LLMs just are as bad at verification as they are at generation. We have a paper in iClear, which actually was written like a year and a half back. It's coming out in iClear. That shows that LLMs are actually bad, and so much so that if you make them verify themselves, their post-facto performance reduces because they can't tell whether they're correct or wrong, and so they will sometimes walk over the correct solution and sometimes give the wrong solution without realizing. Okay? Because it should not be surprising, because verification is a reasoning problem, and it should be worthwhile that keeping in mind. Which also means that the usual problem characteristics that make things hard in life, such as stochasticity, partial observability, additional agents in AI, right? If you want to say I'm working on hard problems, you do things like PalmDP or DEC-PalmDP, where there's basically life is too short to do those things, but you can do it because it's extremely hard combinatorial problems, right? So the question is, they're no easier or harder for LLMs. They will guess the policy for your full MDP, fully observable MDP, as well as DEC-PalmDP, just with same ease and no extra guarantees, no less guarantees. Do you understand what I'm saying? Keep that in mind. On the other hand, background knowledge is extremely easy for LLMs compared to pretty much anything else that came before them. This is the stuff that we're equally impressed that, oh, my doctor was able to put together 3 very different symptoms and say that I have this really rare disease. That's a pretty impressive thing, and you basically go there. That is the kind of stuff LLMs are extremely good at doing, because they have all the knowledge and they can actually make connections. Some of them are wrong, some of them are right. When they're right, you're just very impressed. Okay, so in fact, they're pretty good with no guarantees and some brittleness at providing common sense knowledge, providing domain knowledge, providing theory of mind information, providing analogies, providing anything. Which is why you write papers saying LLMs are zero-shot XXX, where XXX is some random capability that you check whether LLMs are there, and URIPS will take your paper. Okay? There are too many of them already written, but there's still a few left. You can write those. So I already told you, this is all sort of a kind of a setup, and I want to kind of give you some actual results from our work. So as I said, I was in planning. I work in planning originally. So when LLMs reasoning stuff came up, I started trying to check whether LLMs can do planning. By the way, the simplest kind of planning problems that people look at in AI planning community is these block stacking problems. Okay, and this particular one is C is on top of A, B is on the table. You want to put A and B on top. And then you have actions such as stack AB, unstack BC, put it on table, take it from table, that sort of thing. Okay, simple action, simple thing. And people make fun of this domain because it's so simple. Okay, so when LLMs came along and people were writing lots and lots of papers on LLMs can plan, then I asked Karthik and Sharath, and I didn't ask, all of us decided, let's check. In fact, upfront, it didn't even look like it's a worthwhile thing for me to do because I knew they won't be able to do planning. But sometimes it's actually good to show that what everybody is delusional about is actually a delusion. I mean, so we actually got papers because enough people have delusions. So anyway, so large language models actually cannot plan is a 2022 paper that was written 2022 summer or something, and that actually has, I think, at URIPS workshop it was presented. There's a whole bunch of citations, I don't know. And then we wrote additional things in the URIPS 2023 on a more systematic evaluation of planning abilities of large language models of these kinds of planning problems. And we also provided a plan bench which basically you can use in addition to other kinds of planning problems. And the benchmark also contains, so and the bigger point that we came out of that essentially is LLMs cannot do planning in autonomous mode. They can't. And if you do any reasonable study, they will fail, okay? At least on the plan bench. And this thing, Karthik actually, one of his side gigs is to continue checking every new model on plan bench and putting out results. And this one basically has, I'll show you the DeepSeek results later, but this was 2024 with Claude, GPT-4, Llama, and Gemini, etc. And you'll notice that they're not that great on the blocks world side, but they're much worse on the second thing, what's called mystery blocks world. I want to explain what mystery blocks world is. If you want to know whether your friend is answering a question by reasoning or not, reasoning or they just heard about this question before they entered the room, and so they blurted out the answer, how do you tell? Do you understand what I'm saying? So there's this old problem called why are manhole covers round? And the very first time some sucker got asked this question in a Microsoft interview, they had to actually reason. None of you reason because you all prepared on the same damn question bank, right? And so you just blurt it out. And you also, because you're smart enough, you'll say, let me think, and then give the answer. You understand what I'm saying, right? So how do you make sure that they're not retrieving and they're actually reasoning, especially on systems that have been trained on web scale data? What you have to do is somehow come up with problems that they couldn't have possibly seen. So one idea is obfuscating the name. So for example, this is the blocks world problem, domain specification, picking up a block, unstacking, putting down, etc. And then I change the names to attack an object, feast a sub-object from another object, succumb an object, overcome object from other object. It helps that we don't know English that well, so we can write random adjectives, random verbs along with random object names. Interestingly, these two domains are identical. And as Shakespeare said, a block by any other name stacks just as easily, right? And so in fact, any classical planner that solves this can solve this exactly in the same time. The question is, what happens to LLMs? The ones that show something like 30% performance on this die ignoble death on this, 0%, 0.3%, etc. Understand what I'm saying? That is a powerful indicator to you that they are not actually able to put things together. So that was like one of the big things that we actually show in that newspaper. Okay. Apparently, we spent too much time with the blocks world that yesterday or day before I by mistake said Subara Kompati and went to the images. And apparently, I am blocks world myself now. So I have become blocks world, the death of LLMs. Okay. Okay, so LLMs can't plan autonomously. Now, how about chain of thought, React, all this stuff, the prompt engineering hacks? Do they help? Unfortunately, the answer is no. They don't help either. And you think, how the heck is this guy saying this? We have so many papers on chain of thought, and chain of thought is like the greatest thing since sliced bread. Why this thing? So what happens is, most of these chain of thought, for example, provides the procedure and some examples for doing something, at least the JSON-V style chain of thought. And it basically assumes that LLM can follow the procedure. Following procedure is a reasoning problem. It's not actually easy to do it. In fact, a guy called McCarthy, how many of you have heard of John McCarthy? The guy gave the name to the field called artificial intelligence. Why? Because he didn't like Norbert Wiener. Norbert Wiener already had a field called cybernetics. He couldn't stand Norbert Wiener, so he said, anything but cybernetics, let's make a new name, artificial intelligence, and that stuck. Okay, but he's also the guy who invented Lisp, by the way. Okay, he's a pretty big guy. So McCarthy essentially said, the main point of AI is advice taker programs. If you can have a program that can take any advice and carry it out, that's as good, that's the whole goal of AI. So if in fact chain of thought is working, then we are done with AI. And I was kind of surprised because partly I was also job insecurity issues because if AI is over, what will I do? So I wanted to check. And in fact, it turns out that to take something, this is the paper, I believe, he was talking about chain of thoughtlessness and analysis of COT in planning. This is published in NeurIPS this year. An example of what happens there is shown here, where think of this last letter concatenation problem. It's a very simple reasoning problem. You give 3 words, you take the last letters of each word and make a string, that's the answer. The original COT paper essentially used that as one of the benchmark problems and said, if we give some examples of how to do it, its performance increases. And as soon as it increased, they stopped. They wrote the paper. And it has what, 19,000 or 10,000, 25,000 citations now. Okay, what we did by mistake is go further, increase the number of words. If I tell you what last letter concatenation is, and I showed you one example, most of you, even though it's late and after lunch, etc., you can do it for 10 words, 15 words, 25 words. You might complain saying, why the heck are you making me do it? But you can do it. LLMs, on the other hand, die as the number of words increase. You see what I'm saying? So that means they're not actually learning the procedure. I mean, they're not actually following the procedure. It should not be surprising. So interestingly, I just want to say that this is Dale Schurmans, who is a co-author of a Chain of Thought paper with Denis Zhu and various other people. And he gave a talk in ICAPS last year. And basically, this work was done earlier enough. And they apparently said Rao was right. And I'd say Rao is still right. Chain of thought still cannot solve. Chain of thought by itself cannot still solve. It cannot follow procedures. And you shouldn't be surprised. If you're surprised, it's because you're giving it too much credit without checking. Okay, what about you do fine-tuning to improve performance? You can always do fine-tuning. But the interesting question is, it's a well-known idea in computer science that if you want to reduce the online inference time, you solve a whole bunch of problems beforehand, memorize them. Instead of saying memorization, you say memoization. And then when the problem comes, you just throw out answers very quickly. This is what you do in all the competitive exams. You lose your childhood, you prepare memorize a whole bunch of answers such that it becomes like an arm's race between your childhood and the exam setter, and then you do well, right? LLMs have no childhood, so basically they can memorize a lot more than you ever can. And the interesting question is, the reason why we don't always do it is because we care about the cost-benefit ratio. It's understood that you can memorize everything, but if you're only going to be asking 4 questions, basically memorizing 18 million questions seems like an overkill because the amount of time you spent in the pre-training phase has not been amortized over the test phase. This is a well-known computer science issue. We don't ask this now. We don't ask it because we are actually going through a phase where Sam Altman already paid for the pre-training. Why do I care? I just pay the token cost. But from a research perspective, you do have to care about why is this a reasonable idea? And just to give you a sense of how to kind of caricature it, here is a way you can solve a planning problem in a good old-fashioned AI. If I give you a planning problem, you get the domain model, you write a combinatorial search planner, you have the planner solve the problem, you're done. And then people will laugh at you and say, you are not an AI, you are doing good old-fashioned AI. If you want to do AI, current AI, and I call it Llama, LLM AI, and this is what you should do. Again, it's a caricature with some truth behind it, of course. Get the domain model, get the combinatorial search planner that somebody else already wrote, make 1 trillion block solved planning problems, make the damn planner solve them all because you have compute cluster, okay? And then fine-tune GPT-4 with the problems and the answers. And now check them on the held out sample. And if it does better performance, write a new RIPS paper. This is fine-tuning. And it doesn't actually make sense that you use this, and did you check that the cost that you spent in fine-tuning has actually come out in the time when you used it. A part of this will be borne out when a whole bunch of startups that are actually doing fine-tuning will go belly up, because they'll realize that they're spending more time in the fine-tuning costs than making up from the user cost. If not, we will continue doing this. If you understand this, the only difference between fine-tuning in the old days and fine-tuning now is not only do you solve the trillion block solved problems with the A-star search or whatever planner, you ask it not just give the solution, but also give all your mumblings. If you're doing A-star search, you can ask the solver to say, okay, all the open closed list manipulations, blurt it out. You remember you do programs, when you do intro AI star search, you do this trace so that it'll be 5, 6 pages, so it looks very impressive. That's reasoning trace. So you give the reasoning trace and the solution and then fine tune. That's essentially the new post-training, and it has some advantages. The interesting question about reasoning traces, because you asked me, is there's actually a paper called Search Farmer which does that. There's another system called Stream of Search that does that too. So basically, they're making reasoning traces that are actually correct according to these formal solvers. And then they fine-tune the LLM. And so at the inference time, LLM, instead of just giving the solution, it gives some number of intermediate tokens before giving the solution. And those intermediate tokens look in the same form as the traces that it's been trained on. Any of you surprised? LLMs we already know, are wide machines. So they are actually going to get the reasoning trace format right. The question is, are they correct? We actually can check, and hopefully I'll show that in the end, but we actually checked with the A-star search. We can give the A-star search this trace that it generates and say, is this actually a correct trace? Is this actually a correct trace? And it turns out that it's not a correct trace. And it winds up being, most of the time, the trace being correct and plan being correct are orthogonal issues. That's what winds up happening. Okay, so I already told you this. And so the other thing that I want you to understand is, why do people claim that LLMs have planning capabilities if they're doing that badly on mystery domain and blocks work? Part of the reason is, just like in the medicine, there are like two different things, putting pieces of knowledge together, and other is deeper reasoning. In planning too, there are two kinds of issues. One is getting the knowledge of what are the actions, what are the preconditions, effects, et cetera, et cetera. And the other is actually putting together the subplans for the different subgoals in the correct order such that the interactions are taken care of. The first part is easy for LLMs. The second part, they can't do. Blocks world, essentially, second part winds up being very important. So if there are interactions, they wind up dying. But if you actually don't say anything about the planning domain, they may still know what are the actions, what are the possible preconditions, and what are possible subplans for every subgoal. But if, in fact, in the domains where any subplan for any subgoal can be combined with any other subplan for any other subgoal, they can do planning well. Those are the cases planning is just a knowledge issue rather than a reasoning issue. Okay? And it turns out that you can show that is the case. This is from, again, Newry's paper, that if you take the blocks world and remove interactions by essentially saying actions can never get into each other's way, by removing preconditions and removing any delete effects. That means what you do cannot be undone by anybody else. In which case, it's like happiness and joy. It's just a whole bunch of subplans, and all of them can be combined in any which way. And if you do this, as you relax the interactions, the performance of LLMs increases. That's because any arbitrary plan will wind up being correct because there are no interactions. So a cynical way of saying it is they do extremely well in planning tasks when planning is probably not needed, and all you really needed is subplans for each other's subgoals and putting them together. Okay. On the other hand, LLMs are great at approximating knowledge. And then, in fact, we have a Newry's paper showing that the planning domain models themselves can be taken out of LLMs, by basically with the human in the loop. And that reduces the knowledge engineering effort. Okay. I'll skip over this because we have time. I want to spend the next minutes in this part, the system one, system two part, that as I already mentioned, that I want to say that if you want to go from LLMs to a place where they can do correctly on reasoning problems, the simplest idea is test time scaling. Test time scaling is an old idea. In fact, before LLMs, before AlphaGo, game search engines were always doing only online inference. They will essentially look at the board position and start figuring out, doing a limited depth min max or MCT to figure out the. What happened with LLMs is that you try to get by with just system one behavior. And if you bring it back, that's test time scaling. If you start doing some more online inference. The simplest kind of online inference could be as simple as essentially let the LLM, instead of just giving one guess, make it guess multiple guesses and see if any of them are correct. It'll do more work. And if it's a harder problem to guess the correct answer to, then it has to do more number of guesses. And so you take the majority vote. Those are things like self-consistency, et cetera. A better idea that we push is this LLM modulo approach, where you wind up doing a language model as a generator, and then you wind up using a bank of critiques, and they're basically checking. These are some of them are formal critiques that existed before LLMs. Some of them are learned critiques. Some of them are LLMs themselves, but they mostly will do style critiquing, and they can actually critique the plan, and then LLM goes back and improves its guess. Okay, and then this loop continues. And as I said, LLMs themselves can be used as style critiques. And one other thing that I want to mention, maybe I'll skip this, but okay. So one other thing I want to mention is that with the sound verifiers where they're available, you wind up getting guarantees. Because if something is coming out of this loop, it's because the critique said they're correct. Okay? You can, however, and then the kinds of critiques include, as I said, the formal critiques, as well as LLMs themselves being used as critiques. And when you do LLMs as critiques, there are problems. This is the iClear paper I said, that they can actually worsen the performance if it is based on correctness. But they can be used for style. In fact, this is a paper from COMB last year, where we use VLMs to check whether certain behaviors that are already goal-reaching are in the right style in terms of people being fine with it. For example, if I ask the robot to give me a pair of scissors, it gives me the pair of scissors with the pointy end pointing towards me. That is solving the goal, but you just are feeling worried, right? So that's the kind of things VLMs actually can critique, and then you can change it. Yeah, yes. So there's that paper, and then you can also do style, the human mind modeling, mental modeling sorts of questions also are like style things that you can do. It turns out that LLM modulo actually improves accuracy with guarantees. There are results showing that. And one of the other things is things like alpha geometry and program synthesis with LLMs actually wind up using these ideas. They don't call it that. But if you think of program synthesis, for example, you have unit tests. Unit tests are partial verifiers. And the partial verification is what the LLM uses to improve the code. If the code is failing in the unit test, it's definitely wrong. If it is passing, it may be less wrong. And that's what basically happens, and that's the kind of thing alpha geometry winds up doing too. That's about the test time scaling. To get this into the generator, how many of you guys recognize this guy? Anybody? Yeah, you of course will recognize it. This guy is Minsky. He's one of the other guys who was in the conference that named the field artificial intelligence, Marvin Minsky. And Marvin Minsky said, intelligence is integrating test part of generate test into the generate part. Okay, so what you want to do to increase the generator's improvement is, remember if you are doing something like LLM modulo, after it gets the correct answer, you can remember the correct answer, and you can get a whole bunch of problems in the correct answers and fine tune. That would improve the generator. If you also remember the reasoning traces, that is essentially what DeepSeek R1 is doing. So the post-processing that's done, post-training that's done in DeepSeek involves RL post-training and as well as SFT post-training. And the one thing that I want to do, two things. One is, in the case of DeepSeek, what happens essentially is they had to generate web for reasoning data. There is no web for reasoning data. We wrote web for normal factual data. The web for reasoning data involves solving more and more problems and remembering their solutions. That is synthetic data being solved. So in essence, they are generating additional parts of reasoning web by converting compute into data. So compute really is data if you have verifier. And that's an interesting way of checking how you are making a retriever solve reasoning problems by essentially compiling more of the reasoning problems by solvable bits. The other thing that I want to mention is, you can ask me questions after this. The RL is made a big deal about in DeepSeek in compared to SFT. It turns out it's really hard, it doesn't do anything much. All it does is the base model already generates the traces and verifier checks which are correct. And SFT would have waited for all the correct traces and done one change of the LLM policy. RL does it piecemeal. So if you do iterative SFT, it probably is likely to be just as close to RL. So it's worthwhile understanding that. You can combine test time scaling and post-training, although R1 doesn't combine it only does post-training, it doesn't do tech-time scaling because it's actually a pure LLM in the inference. O1, I have no idea what it does. So Noam Brown, when he came up with the O1, he basically wrote this thing saying that Rav said certain Bloxworld problems can't be solved, we can actually solve it now. And so we actually paid $8,000 and checked plan bench on O1, and those are papers, one of them is coming in TMLR, that basically show that the performance improved for sure. It's a better generator. O1 is a much better generator than GPT-4, but it does still have the same problem as the plan length increases, accuracy worsens. Furthermore, it's actually much better at gaslighting you. In addition to hallucination, it also can do gaslighting. We gave a bunch of unsolvable problems. It will say they are solvable, and it'll argue with us. And if you're one of those people who are easily intimidated, you'll say, maybe you're right. I mean, after all, you're coming from OpenAI. So in addition to gaslighting, you have this, in addition to hallucination, you have gaslighting problem. There's also a whole interesting issue of cost considerations inside of a continuation of the original cost considerations for fine-tuning I talked about. DeepSeek R1 is indeed competitive with O1 for much less time. Please give me 5 more minutes so that I'll take the 5 minutes and complete it. So the language models on the plan bench, DeepSeek does reasonably well corresponding to O1, but it's much cheaper. And then one other thing is we can actually use DeepSeek or O1 as the generator and do LLM modulo, and it becomes LRM modulo. And we did the LRM modulo, and we can actually improve the accuracy of O1 and O1 preview with guarantees, because you then make it generate and then still making it go back because it's not correctly verified. So that's the other thing. And then fine-tuning on the derivational traces, the thing that I want you to understand is what's happening currently between O1 to O3 and R1, et cetera, is they are incrementally converting the verifier signal into the base LLM. So in R1, originally it starts with a base LLM, and then it does a bunch of this, let it generate traces and pick the correct ones, and then either supervise fine-tune or do RL, and then you get what they call R1, which can then be used in the distillation phase to get to R2. So that basically increases the number of extra problems it can solve. So it's been said already by people that O1 is actually generating data for O3. And similarly, R1 will be generating data for R2. Okay, and so that's a way of understanding what I was saying, which is you're converting compute into reasoning data. Okay, one last thing is that I said reasoning traces. You should let me answer this because you asked this question. Reasoning traces don't have meaning, I said, but you say, how do you know? English can be hard to check whether it has meaning or not. But I said search farmer actually uses formal solver, so you can check the search farmer results, right? And if you take DeepSeek, by the way, as I said, it gives 35 pages of result for like a simple Bloxworld problem. It goes on and on like that. You guys now understand? Now, are you impressed that it's correct? In fact, the number of pages it outputs has nothing to do with the answer is correct or not. But if you use the ones which are formal solvers, then the formal solvers have specific, very weird-looking traces. This is a star search trace about changing open and closed list. And they actually check that that also improves performance. The advantage is you can actually check if, in fact, the traces that are, search farmer outputs in the inference is correct or not. And when we checked, we find a huge number of cases, the plan is wrong, the reasoning trace is wrong, the plan is correct anyway. That's because nobody checks the reasoning traces, which makes you wonder if, in fact, reasoning traces at the reasoning level are not actually important, do you care about training with the correct reasoning traces? We did that experiment day before yesterday, and my students sent me results. It turns out you take reasoning traces, correct reasoning trace with the correct solution for problem 1, correct reasoning trace with the correct solution for problem 2, swap problem 1 put here, problem 2 put here. Now it's wrong reasoning trace for the problems. I train LLM with that, 100% accuracy. It's the same accuracy as before, which basically means the mumblings don't mean anything at all. And if the mumblings don't mean anything, then let's admit that. And basically, you can actually use it as, avoid using it as an albatross or a cognitive flaw enhancer. And then that you could actually do things that are coming more directly from alpha 0 and mu 0. You can ask me about that, I'll tell you. And then when Washington Post asked me about DeepSeek, I told all this and they wrote this up. If you're more interested in more of this and you have extra time, listen to this ML Street Talk stuff. And then I also gave like a tutorial in ICML as well as a ACL talk that also has point. And this is a summary. I want to again show my students because those are the ones who actually did all the work. And then I'll stop, thank you, and ask me any questions you have.
So maybe the question is, can humans reason?
Can humans reason? Depends. First of all, you have to define. And in fact, one of the things that I would argue is civilizationally, we developed, human civilization can reason, for sure, because we developed things like logic, we developed things like formal procedures with guarantees, and those actually have guarantees, and we, humanity, came up with it. Okay, this issue, one interesting thing that I will answer your question in a very interesting cognitive flaw that all the major vendors use, which is if you ask them, can it do, there's a guy on Twitter who basically, whose life, just like Karthik's life, is whenever a new model comes, he does X by X digit multiplication, N by N digit multiplication, and see when it starts being wrong. And by 20 digit multiplication, they're all wrong. Even O3 and et cetera. When they say it, then the commercial vendors will say, but do you know any people who can do that kind of multiplication? But do you know any people who can do frontier math problems? Do you know next to you who can actually solve frontier math problems? That's very unhuman-like to do frontier math problems. But we take credit for that. And yet we are saying multiplication when it fails. So I would push back on taking credit when it works and saying there is no blame whenever it doesn't work, saying normal humans can't solve it also. Normal humans can't do most of the things that LLMs are being used to solve right now. And so it makes sense to think in terms of things with formal correctness guarantees and checking whether they're actually able to do better. So it's a different issue from whether can you do better than humans or can you impress humans that you can do reasoning. Many of you have heard of Eliza, the chatbot, which was like in 1962, and people were already pouring their hearts to it, thinking it is actually listening to them and giving real advice when it is actually just doing rule-based stuff, right? That is not going to be a good way to decide progress. You have to provide better means, and that's what I would say.
I wouldn't argue civilizations can't reason either. If you've been watching the news for the past few months.
That's a very, very different story.
Yes, so I'm going to bring a heavy hitter to ask you a tough question. Jun Sok-cho in our department.
Right, so thank you for the excellent and very inspiring talk. So I always have this question about the whole field of AI. We constantly come up with solutions so that AI becomes better and better. And suddenly then we have to publish some more stuff. So we think of something that the current AI cannot solve, such as the mystery block walls problem, right? And then eventually someone will solve it, right? So my question is, can large language models come up with their own questions? For example, if you ask it, can you come up with a question that you cannot solve?
First of all, they're very good at coming up with questions they cannot solve because they cannot solve most of the questions we give them. That's a different point. I would just say that the idea that in AI, in fact, even when I was a grad student, we would say, this was 1984 when I was taking the Intro to AI class, 1984. I know most of you weren't born. We would say that if it can be done, it's not AI. Right? It becomes just boring computer science databases, software engineering, whatever the heck you want to call it. So AI, by definition, is stuff that's still not done. But that's kind of true for science. Classical mechanics, until it was done, we had no idea. Until Galileo told us about, gravity not caring about, the shape of the object, etc. We didn't know. But once we figured that out, we said, oh, we still don't know this other stuff. So science always talks about do we know what we know and what else don't we know? And on the other hand, if I'm doing startup, I'll just say I'm done and give me my exit strategy, I'll make the money. But science, it's just normal, okay? And for the LLMs, the question of making up problems, you can actually, in fact, I used to do this, first of all, for certain kinds of problems, you can make up problems very easily. You can make up new multiplication problems, right? Because there is a format for it, and you can just write a big number of digits, another big number of digits. You just don't know the answer, right? Right? So making the problem and finding out whether whether it has an answer are two very different issues. And actually getting problems that are interesting in a research advancing sense is essentially all what research is about. Right? It's not just solving. Solving is what you do as an undergrad. Asking right questions is what you do as a grad student, right? And they can ask a whole bunch of questions, and then it's not very clear to me what that adds because they don't necessarily know which one. I mean, there's no actual guarantee that there is a connection between the questions being asked and the way the field will progress.
Yeah, a question back there.
Hi, Professor. My name is Govind. I have a question about the verifiers in the LLM modulo system. So what exactly is like the machinery of the verifiers? Are they problem specific?
So many problems have, you can have different kinds of verifiers. So actually the most interesting general verifier is Python interpreter. Okay? If you are trying to come up with new code, basically, LLMs didn't write the Python interpreter. Python interpreter has this beautiful advantage that it can take any Python-looking code, run it on a given input, and give what the answer is. And then given the Python input and a bunch of these unit tests, you have a verifier. That's a partial verifier. The more the unit tests, the more it covers. In certain other cases, like correctness of a plan, correctness of a schedule, they can be task-specific verifiers. And there is this other interesting question that many really hard problems don't have a single verifier. So when NASA sends people, currently rovers to Mars, it doesn't have verifiers to make sure that the plan is completely correct because that's a crazy number of factors. But think of the NASA people saying, since we can't verify anyway, why don't we guess and send one thing? That's not what they do. You verify the pieces that you can still verify. So in a plan, there can be the resource constraints that you can verify, the causal correctness you can verify, et cetera, that may still make the plan incorrect, just like checking all the unit tests may still make the code incorrect. But if it actually fails the unit test, it definitely is incorrect. That's the point of verification. That's basically the point of what you do in terms of guarantees, which is at least catch the errors that you can catch. And that's how you increase the density of the correct solutions, which then the LLM is now being retrained on. Okay? And basically, for many areas, the way I would argue, and this is a thing that you should push back, obviously, you should think about this. I would argue that what's happening in reasoning is essentially taking existing verifier technology that we built in different ways, either as a Python interpreter, or as a planning interpreter, or as something else, and taking that signal seep into the generator. And we have a general purpose generator. That's the LLM technology. And you're doing this by converting, when you do that, essentially, you are essentially converting compute into data because you have verifier and you can keep generating more guesses. And the better the generate is, you will do less amount of work to generate the same amount of quality data.
Sorry, could I just ask a follow-up about that? Oh, no, okay.
We're out of time. Sorry, Vint. So the reports are due in about less than a minute. So make sure you all submit. Let's wrap up the discussion here. There is a reception in Peterson 118. So Govin and all of you, you're welcome to join us for a snack and an opportunity to continue asking questions. So let's thank our speaker one last time.
So I think I will be here at whatever that reception is, and I don't plan to eat anymore. So if you have any questions, please ask me there.
Thank you.